Hello students, welcome back. Now let's go to section 5, interval estimation for binomial proportions. Here's a reminder on the normal approximation theorem for binomial distribution. For binomial sum, we have the expected value n times p and the standard deviation of square root of n p1 minus p. For binomial means, you get the expected value of the same p, the proportion, and the standard deviation was square root of p1 minus p over n. Remember this way back from chapter, I think it's coming from chapter 3 and then reinforced in chapter 4, I think. But if you want to apply the central limit theorem, you can go back to this kind of computation all the way back. Let's see if we have anything here. Okay, for a Bernoulli trial, that is doing just once with success and failure, 1 for success, 0 for failure, it is easy to calculate the expected value like this. 1 for success, 0 for failure, and then calculate the variance, deviation squared times probability, deviation squared times probability. After simplification, you get p times 1 minus p. So taking the square root, we get square root of p1 minus p, like that. And then let's apply the central limit theorem. Or actually, we don't even need central limit theorem, actually. What we need is this property. We have simple random sample. So x1 through xn are independent and identically distributed. So the variance of sum is sum of the variances. And then divide by n, we have sigma squared over n, like this. And taking the square root, you get sigma over square root of n. So what is it? Sigma, which is square root of p1 minus p over square root of n. So we end up with this. So you can deduce everything using the theory of point estimation, theory of independent and identically distributed random variables. But that's a kind of overkilling, so let's accept this as a formula. SE is square root of p1 minus p over n. Oh, I already have SE down there, so let's go down there. The summary version. The binomial proportion can be approximated through the normal approximation centered at the expected value mu, which is same as p. And then the standard error is square root of p1 minus p over n. Oh, I already have mu is equal to p, so all right. I don't have to specify here. So down here, expected value, mean, the center is p, the probability of success, and standard error is square root of p1 minus p over n. Remember these, especially the latter. Arguably, the formula number 2, maybe formula number 3. Okay, let's do a confidence interval problem. In a poll conducted by Harris Interactive of 1,179 video gaming US youngsters, 8.5% displayed behavioral signs that they maybe indicated the gaming addiction. 8.5% displayed behavioral signs of game addiction. So that's the best point estimate. And the real proportion must be somewhere close to 8.5%, give or take. That's something we are looking for. So we are doing an interval estimation. You can create picture like this. And then normal approximation picture like this, centered at 8.5%. So 0.085. And we want 95% confidence interval. So here, there, and I have 95% in the middle. So the other 5% must be shared by the left and the right. So this part here is 2.5%. And this part here is another 2.5%. Really lousy picture. Let's remove it and let me show you the end result. Okay, here we go. So center that the observed mean of 0.085, that's the observed proportion, and 2.5% here, 2.5% there, 95% in the middle. And then you're going to find out the z-score associated to the left-hand side shading of 2.5%. So let's say this is left-hand side endpoint, L minus end minus center over SE. So this is L minus center 0.085 over square root of P 1 minus P over N. That's a formula, isn't it? And P is 0.085 and 1 minus of that divided by 1179, and that should be approximately equal to the z-score associated to 2.5% here. What is that quantity? Well, let me open up the z-table. It's here. Yeah, shade is to the left, and let's look for 2.5%. Let's see, it's gotta be around here. Yeah, right here, 2.5%. Negative 1.96. So negative 1.96. So from here, you can solve this equation and find out the L value. So L minus 0.085 is approximately equal to negative 1.96 times the square root . And then of course you can find out L value by flipping this to the other side. If I do that, this is what I'm going to get. Punch in the calculator, you're going to get whatever you want to. It'll turn out to be this. 0.069, about 6.9% if you do it right. So from the center, I have to go to the left by the margin of error, z-score times SE. From here to the left, the margin of error, z times SE. What if I want to find out the right-hand side? It's the same because the normal picture is symmetric. So R for right-hand side, and then this is going to be positive, and that's it. Change this to plus, and punch in the calculator, you're going to get something, and that something will be this number, 0.1009 something, about 10%, or 10.1%, or something like that. So that's going to be your 95% confidence interval. There is 95% of chance that the real proportion falls in that interval. Here's a computation. You can use bracket like this, or parentheses, or any kind of expression. Okay, so much for the confidence interval. How about the confidence bound problem? Look at this. No less than whatever percent of youngsters show the sign of game addiction with a 99% confidence level. See the difference? Not some percent to another percent, not somewhere to somewhere. We just have 1% point. no less than whatever percent, that is more than or equal to this percent point. We're talking about something like this. This number to whatever. Of course, you don't really get infinity here. Infinity is coming from the normal approximation. In reality, proportion never exceeds 1. So the right-hand side is not that important. This one is important, the lower confidence bound. In terms of the normal picture, you get something like this. So here we go. Let's do it again. Okay, horizontal line, we have the normal approximation picture. And then this number is the lower bound. And then this is the observed proportion, 0.085, right here. And then this proportion here is 99%. And the other 1% comes from the left-hand side here. My goodness, what a lousy picture. Let me get out of here. Okay, here is better picture. You see, only here, the left-hand side endpoint or the lower confidence bound, 99% here, 1% there, and the z-score is n minus center over SE. And what's the end? It's L, the lower confidence bound. And what's the center? 0.085, the expected proportion. And what is standard error? Square root of p, 1 minus p over n, isn't it? So this is going to be 0.085, and 1 minus of that divided by 1179, and that is your z-score. Nothing is accurate in statistics, so let's change this into approximate equality sign. And that's supposed to be equal to the z-score associated to 1%. Z-score associated to 1%. Let's look it up. The stat table. No, not this one. Yeah, this one. Previous table. And look up 1% here. This one's the closest. You see, 0.0099. And that's negative 2.33. Negative 2.3 and 3. So this one is equal to negative 2.33. And we can easily find what L value is. Flip this denominator to the other side, and then flip this center to the other side. You get L is approximately equal to the center, 0.085, minus 2.33, the z-score, times the standard error. 1 minus that, divided by the sample size. Punch into calculator, you're going to get something. And if you do it right, you're going to get 0.0661, that is 6.61%. So at least 6.6% of the students are showing the sign of video game addiction, according to this poll result. Here's the computation, by the way. Here's another problem, and that one is about sample size, but I'm not so sure if I have enough time, so let's stop here and let's complete section 5 in a separate video.